What is that?
What page we got here?
213. Okay, let's take a look here. We got lots to get through today. See if we can get through 3 or 4 problems. Okay, everybody take a look at this problem. Peer over shoulders, whatever you need to do. Take a look at this problem here. So this, and I'll read it. A man is in a boat 2 miles from the shore, from the nearest point on a coast. So he's out in the ocean somewhere. He is to go to a point Q 3 miles down the coast and 1 mile inland. Okay? If he can row at 2 miles per hour and walk at 4 miles per hour toward the point, toward what point on the coast should he row in order to reach Q in the least time? So we're minimizing time. So the picture, and they kind of even give us a picture here. So, upper right.
Oh.
Okay, make sense? Oops.
I said the yellow was good. Then where did you take it? Don't worry about it.
Right, 3 miles downrange. Okay, and this distance right here is 2, and that distance is 1, right? Okay. So he goes faster on the land. This is the ocean out here, right? This is the beach. Okay. So, what do you think? I mean, we're going to figure out what the answer is, but what do you suppose he's probably going to do? What's your intuition tell you? He's not going to go in a straight line probably, right? Yeah, he's going to probably want to get out of the water more quickly because he's slower there, right? Yeah. So he can walk more quickly along the land. So he's going to take maybe a path like that, right? Something like that? Okay. So you want to know what point he's going to hit on the land, right? So what do you recommend as a variable here? Or where should I put the variable? On the beach. We want to know how far down range is he going to aim, right? So we could call this distance right here, for example. Let's call that x. So that's the point where he's going to aim, right? Now we got to come up with our primary function. Okay, so the distances aren't hard to find, right? We know that if this is x and that's 2, what's the blue distance? X squared plus 4. Yeah. Okay. And what's this? Getting a lot of colors up here. What's that green distance going to be? 3 minus x. Good. So we don't even need a second variable here, do we? 3 minus x. And if that's 1 and that's 3 minus x, what's the orange distance? Okay, so square root of plus 1 squared, which is 1. And if we expand that out, what do we get? X squared minus 6x plus 10. Okay, so there's that distance, right? If I FOIL that out and add that to it, right, I just get, a squared plus 2ab plus b squared. Okay, we'll flip it around so the x is first. Okay. All right, so But we're not really looking for distances, are we? If we wanted to minimize distance, what path would he take? Straight line, right? He'd take a straight line, but we're not doing that. We're trying to minimize time. So we have to come up with a time function. Now, what's the relationship between distance and time, and speed or velocity? Velocity or speed equals what? Distance divided by time. You just think of the units, right? Velocity would be something like miles per hour, right? So number of miles and number of hours. So distance over time. So if we solve that ratio for t, what do we get? T equals d divided by v, right? Because I'm just trading places in this ratio. So really, this is kind of a weighted distance in a way when we're trying to find time. We've got the distances, but they're divided by this travel speed, right? So really, this first distance right here, if we talk about the time it takes to travel that distance, and we call that, let's say, just T1, what is T1? Time it takes to travel through the ocean. We know the distance, right? And what did the book say? I think it said he travels at 2 units per unit. I mean, I don't know what the units are, miles per hour or something like that. Miles per hour, okay. So if he's traveling at 2 miles per hour, what are we going to get for our time? Yeah, always divided by 2, right? So we just get this distance divided by 2. Right? What about T2, we'll call it. Same idea, right? Just going to be that distance divided by, I think he goes 4 miles per hour on the land.
Yeah.
So divided by 4. And then the total time is just the sum of those 2. So we get our time function. Time as a function of x is just that. What's our domain going to be in the picture? X is the independent variable. 0 to 3, right? Obviously, he's not going to probably aim for a point backwards down the coast, right? He's not going to overshoot. I mean, that's going to not minimize time. So, 0 to 3. So now all we have to do is a little calculus, right? We've boiled this down to where we can just shift into calculus mode, make a table. Thank you. Here. All right. So let's differentiate. How do I differentiate these? Square root, what do I do with the square root?
Like 1/2.
1/2 power, right?
Yeah.
Okay, so we'll think of these as being 1/2 powers, square root. So if I differentiate using the chain rule then, so I've got 1/2 times 1/2 is 1/4, right? So I get a 4 on the bottom. And what's the chain rule tell me about?
It's 2x.
Okay, but I've got 1/2 hand to the
Oh, yeah.
negative 1/2. What's a negative 1/2 power?
Goes down the bottom.
Goes to the bottom. So I got a square root on the bottom. And now I've got to differentiate what's inside, right?
Yeah.
So what's the derivative of x squared plus 4?
2x.
2x, okay.
That's where I was.
Okay. Will be okay with that? Okay.
Yes, I am.
Plus, same deal over here, right? Got just hand to the 1/2. So 1/2 times 1/4 gives me an 8 on the bottom. Hand to the minus 1/2 puts the square root on the bottom. Times, this time, what do I get on top? Good. Okay. And so we can simplify that just a little bit. How about if we divide top and bottom of both of those by 2? Sure. So we get x over 2 times the square root of x squared plus 4 plus x minus 3 over 4 times that other square root. So is this going to be undefined anywhere? It's not going to be, and it would have been easier to see maybe if we had left it like that, right? Because would you agree on our domain from 0 to 3? Yeah, we can't, I mean, in fact, we can't have a negative anywhere, can we?
No.
Because I've just got some quantity squared plus 1, right? So it's not undefined anywhere, but we do need to find where it equals 0, don't we? That's right, so
No.
when is that going to equal 0? How are we going to solve an equation like this? This is kind of a, oops. This is kind of a tougher one. It's solving a these are good. We don't do these very often. Yeah, okay, good. Good, so we'll just add the second term over to the other side.
And then cross multiply.
And, yeah, cross multiply. Good. Okay, so if I do that, I'm going to get, on the left side, we'll keep this one. On the right side, I'm going to get the opposite of that.
You to show up.
525.
Yeah, okay, so we're gonna,
Smackdown.
so on the right side, we're going to get the opposite of this term, right? Rather than distributing a -1 through, well, what happens when I distribute a -1 through? Negative x plus 3 or 3 minus x, right? We'll just multiply the -1 through. So on the other side then, we're going to get 3 minus x over 4 times that big square root.
Oh, I see.
Okay, questions? Okay, so now all we have to do is just square root, right? I mean, cross multiply, right? Okay. If I cross multiply, this is going to be kind of ugly. I'm going to get,
I like ugly.
yeah, I'm going to get 4x times square root of x squared minus 6x plus 10 equals, yikes, 3 minus x.
Hey, thank you. She was better not be able to say it.
Okay, and really, okay, I have another suggestion here.
Sure.
That's gonna be kind of tough. Let me ask you this: what's our general strategy for dealing with square roots, solving equations involving square roots? Yeah, right. We always try to isolate the square root and then square both sides. Remember that back from honors algebra 2? Okay. So, how could we do that? Yeah, isolate the square roots on one side. So right now I've got a square root over here, I've got a square root over here, but if I cross multiply, what I'm saying is we can avoid doing that in 2 steps. We can do it in 1 step. Remember, if we have a ratio equation, we can always just exchange diagonally.
Yeah.
Right? So what if we do that? What if we exchange diagonally here then? We're going to get 4 times the big square root over 2 times the small square root,
Oh, I'm with
right?
What happened to the x?
and then the x is gonna end up down here, okay?
I didn't know you could do that either.
What's that?
I didn't know you could do that.
Yeah, oh, yeah, that's a great little trick, yeah.
I didn't know that.
Yeah, if you have a ratio equation, you can always exchange diagonally. It's equivalent to cross multiplying and dividing, but it's a lot quicker.
Wow, alright.
Wow.
That would've been nice for 2 years.
So we can do a little reducing, right? This just becomes a 2. And then what's the important property here? If I have the square root of a over the square root of b, what can I do with that?
So you can just combine it.
Yeah.
Put it under one bracket.
I can absorb that as one square root.
Whatever it's called.
Okay. Wow.
That's vocabulary.
That
Is that what
is.
it's called?
How about that? Okay, so then all we have to do is just, if I square both sides, I'm just gonna get rid of that radical on this side, right? So I end up with, if I square both sides, the 2 gets squared. So I'm gonna get 4 times x squared minus 6x plus 10 over x squared plus 4, right? Equals, and I gotta square this side out too. So this side I'm gonna get, we probably should have just kept that as we might go back and complete that square again. Because we're gonna get an x minus 3 squared. 3 minus x squared and x minus 3 squared are the same thing, right?
Yeah.
Over x squared.
Wait, say x minus 3 squared is the same thing as what?
As 3 minus x squared.
It's just
Oh,
the
Right, because think,
negative.
if I wrote that as if I square, that's the same, this is the same thing as saying negative x minus 3, and if I square that whole thing,
It's because of the
Oh,
square.
there you
the one negative 1 squared goes away,
Oh,
right?
yeah.
go. I see.
Okay. And so now, do you see where maybe we're going with this? So now, it's a little bit ugly.
Something like that. I like it ugly.
Okay, now what? Well, this is a bad one. It's kind of a tough one. But we can do this. What do you suppose we need to do here? Now, would you agree that if we just cross multiply here, what's the biggest power of x I'm gonna get? X to the 4th, right? So worst case scenario, all we've got going here is when we combine like terms, we're just gonna get a quartic polynomial. Right. Well, because when I cross multiply, I'm gonna get the biggest term I'm gonna get is x squared times x squared this way.
Gotcha.
And I'm gonna have an x squared there times an x squared there, right? So worst case scenario, we're getting a quartic polynomial. So we're gonna kind of look ahead a little bit with this. That's gonna be sort of hard to solve. If we could go that route, and maybe this would be kind of a question where we could even do a little graphing calculator cheating and just find the roots that way. Maybe it's easy to solve. Maybe it is. Maybe it's a quartic polynomial that's missing some terms and we can solve it just, being tricky. Maybe. So that's one way we could go. The other thing we could potentially do, remember what this really is. And this is obviously this question, I'm surprised it's in there. This is kind of a hard one. Did you guys do that one? No. Okay, maybe I didn't assign that one for a reason. This is a pretty hard question. If we go back, remember that x squared minus 6x plus 10 is really just that, right? That's where we got it. We expanded it out, and if we reverse that expansion, if we factor this, we end up with, I'm gonna go back and change it. So if we rewrote this one as x minus 3 squared plus 1 instead, now look, I've got x minus 3 squareds in there. That might be helpful. Okay?
Oh dear.
All right. I don't know if this is worth going any further with or not, but we'll just see what happens. If I cross multiply here,
You don't try it.
Where is it?
cross multiply. wanna see if we can do this.
Me too.
Right, just distribute the 4x squared. Okay. Okay. Next. Subtract everything over to this side. So this is a like term. See if you guys can just follow this a little bit. This is, you'll end up doing stuff like this someday, so. We subtract that term over there. That's gonna give us, isn't that just gonna give us 3 of those if I subtract that one from the 4 on this side? Okay? And then here, okay, we're just gonna get,
Reduce optimization rates.
so that's kind of a bummer. That didn't work out quite as well as I hoped it would.
Spoil it. Spoil it.
Darn it. I was hoping that would work out a little better. I had high hopes for something there, but it didn't pan out.
On to the next big word.
Okay, so our only hope here would just be to expand this all out and just solve that polynomial.
Let's do it.
And if it doesn't look like it's an easy one to solve, we would just use technology to do it. We're not gonna go, at this point in calculus, there's no way, did you guys even do, like, last year, the method of, well, like techniques for solving analytically polynomials? Because it's, I think it's kind of a waste of time in pre-calculus now to do that, because nobody ever does it anymore. I kinda doubt you did.
I like the calculations. It is.
All right, so, catch, make sure I don't make any mistakes. If I expand that out and distribute the 3x squared, I'm gonna get what? 3x to the 4th minus 18x cubed plus 27x squared, is that right? Double check me. Minus,
Oh, yeah, that's right.
is that all right?
Yeah.
Okay. X cubed, it's just that one. Lots of x squared, so 27, so those cancel. X is just that guy? Oh, that's pretty bad.
They're all those are by 3. Let's get rid of that.
That's not really gonna be factorable.
Did you, what was that?
Let's take out a 3.
Take out 3.
We could take out a 3.
That's what I'm saying.
Yeah, you take that.
Well, this should be an 8.
Yeah.
Should be
What, did I mess something up there?
8x.
Oh, whoops, 8, yeah, you're right. Oh, thank you. That wasn't bad. Okay, and at this point, we just throw that in a, how would we find, with the graphing calculator, I guess this is a good question, how would we find the solution to that with the graphing calculator? What are our options? Okay, what is it?
I can't remember.
Yeah, there we go, so we could use polynomial solver, right?
Yeah, the little table.
Okay, we could also just graph the function and look for the x-intercepts, those are gonna be the real zeros, right? But that is gonna be really, factoring that is not, we could do this, but it's not anything you guys have ever seen before, so it's not gonna mean anything.
Do it.
No,
No, we don't need to. We have to use,
See a number.
we have
Just
to-
make something up for me. I need to be satisfied.
well,
Yeah, I
what,
know.
the way, if we want to do this completely analytically, what we'd have to do is use the rational root theorem. Have you learned that?
No.
Yeah.
Okay, you'd have to use the rational root theorem to find all of the potential rational zeros of this thing. You'd go through, so that's just gonna be, it's gonna be all the factors of 12, positive or negative factors of 12 divided by 1. We'd run all those through synthetically to divide out factors and whittle this thing down. That's how you'd have to do it.
Let's do it.
Do you really want to?
I want an answer.
Let's
do this. Let's do
I would
it.
like
Using
an
up
answer.
another page, which is useless.
All right, we can do it.
20 minutes.
What's that?
We have almost 20 minutes.
Okay, so let's try it. All right, so if we use the rational root theorem, the possible zeros of this thing, what are all the factors of 12?
1, 2, 3,
1, 2, 3, 4, 6, and 12 is a ton of them, right? So we're gonna if you look at all those numbers, we'll run those through synthetically. So if we synthetically divide each of those into this, whoops. Remember this?
Yeah.
So we're gonna get 1,
We're literally
negative 6, 9, 8, negative 12. And let's start easy. Now those are pretty good numbers, so I think we'll get some out of this. So if we run like a 1 through, what do we get? So we get 1 times 1 is 1,
Negative 6.
negative 5,
Oh, 5, okay.
negative 5,
Kim's
4.
already lost.
And that actually works, doesn't it? So we struck Fader on the first one. So 1 is an answer. Okay. So 1 is a solution, right? And that leaves us with the polynomial now, 12 plus x minus 5x squared plus x cubed.
Well, there's something like if you looked at the highest order, it would, you could tell how many there were, or.
Well, yeah, it's right, it's 4, so there are 4 complex solutions. The imaginary ones have to come in complex conjugate pairs. So you've either got 4 or 2 or 0 real solutions, guaranteed. So we know that we've got at least one more. So then what would we do now? Well, we do the same thing again, right? This is kind of cool. Did I show you guys nested synthetic division? Oh, this is cool. Okay, this is worth seeing. So now we can just take, look what we can do. See, we've got a new polynomial, and there are the coefficients, right? Right? Yeah. Yeah, and so 1 worked. We could try 1 again. It could be a double root, right? We could try it. Probably it doesn't look like it's going to work, but we could try it. So bring down the 1. 1 times 1 is 1. Negative 4. It's not quite going to work. Negative 4, 0. So it's not going to work, is it? So now 1 is out off the list now. This is kind of fun. Math is just kind of fun to do, isn't it?
The easy math is fun.
Oh, easy math that's no challenge. Okay, so let's try negative 1. Let's do a negative 1. Not gonna work, is it? Not gonna work either, okay? Okay, so now we can bring down, let's try it 2, how about? We'll start, use the small ones, those are easier. So 2, 1, 2, negative 3, negative 6. That's gonna work, isn't it? Yeah. Oh, no, it's not, never mind.
Negative 2.
We're not looking at that.
Let's go.
Negative 2,
No.
no good? 2, negative 7. It's not good, is it?
Very tough.
14, no, no good.
3.
Very tough.
Okay, we did 2, how about 3? We'll try 3.
It's not good. I'm doing it right now.
Okay, so let's do negative 6.
Negative 2.
No good.
So it could be negative 3.
Okay, now one thing's probably occurred to you that maybe, what if the roots aren't rational? You know, what if they're irrational?
Well,
So
then
it could
we
be.
can just stop.
Okay, then the other technique, well, I think we're gonna get this. Then the other technique is actually a calculus technique. It's something I skipped over in the book. It's in this chapter. It's called Newton's method. And I'm not enough time to show you today. In fact, I might come back. That might be kind of an end of the year thing, because it's really good. It kind of shows you how your graphing calculator, how it models functions to find zeros in a way. It's pretty cool, but it breaks the flow of what I want to do right now. Did we do -3?
No.
So run it through. Is that going to work? -8. No, it's not going to work, is it? -8 times -3. That's not going to work. -1. No, that's too big. So I think this thing's starting to get out of control now. It looks like a lot of these aren't going to.
Well, there's gotta be one.
Yeah, there has to be one more real one at least. But none of these are working.
3, 6.
Wow.
Hi.
Just.
So these are getting too big. 36, that's too big, right? The big negative ones aren't looking good. You can kind of see a pattern though. 6 maybe? Has anybody tried that?
Zero?
JJ.
6.
6 wouldn't work.
No. No. Oh, God, no.
That's not gonna work. Yeah, I think there's only one easy one. So we found the one easy one.
So the rest of them are complex or whatever they're called.
Well, they're gonna be irrational. Right.
Irrational, whatever.
They're gonna be irrational. Okay, let's see, but what we could do. Okay, I don't, so it's hard for us to find more. We did find one potential critical number. Do we even know that it works?
No.
How come? What did we do back here?
Square root.
Because we squared both sides, didn't we? So we'd have to go back to the square root equation and just verify that, was it 1?
Yeah.
That 1 even works. And I think it's going to. That's gonna be the answer, I'm sure.
Yeah.
So so we get, let's see, 1 minus 6 plus 10, so what is that, 5? 2 times square root of 5 over square root of 5 is just 2, right? 2 over 1 is 2, so it works. So we know it works. The other thing we could do with this, and I think we're starting to get to the point where we have to just talk about what we could do, because we're gonna run out of time. On our table, if the other option is we could look for the second derivative, right? That's not very pretty.
Let's do it.
But the other option is if we look for the second derivative,
Sorry.
the second derivative is another possibility that might give us easier zeros, right? Because if we knew where the zeros of the second derivative were, we could piece this thing together. If we know that we've got, for example, we made a table out of this. Now think about this. If we did right, so on our domain,
Double prime.
from 0 to 3, we had a 0 at 1, right? If we knew the sign of the second derivative, and guaranteed it's going to be what? It's going to be positive, isn't it? Okay, it's going to be positive. Now, if the second derivative didn't change concavity anywhere on our derivative, what would that tell us? Or on our domain? That's got to be the absolute minimum, doesn't it? Right? So there's other ways we could go about this too. We could start to look further down the table where the polynomial gets smaller, because every time I differentiate that function, I'm going to get smaller powers, right? Okay. Although that's going to be a pretty nasty derivative. Okay. Now, okay, maybe this is the opportune time to show this to you. I've been holding off on this. But we could do this whole problem on our calculator with doing no calculus too. Can I do that?
Hallelujah, yes.
I'll show you. So if this is the original function, you're gonna, now, you can't, I will eventually give you a graphing calculator test where you can get an easy A by just knowing how to, because I want you to know how to do this. I think I'll do it on this one. Nah, I won't do it on this one. Too soon.
It's not too soon.
But watch this. This is a way to do the calculus, because really all the table was for was to generate a sketch of a curve, right? Okay, well, your calculator does graphs of curves pretty easily. So if we go up here to the Y editor, see what I'm going to show you? Don't throw things at me when I show this to you. So here's our function.
Careful, that's got sharp stuff on it, right?
We got the square root of x squared plus 4 divided by 2 plus, what's that other term? Square root x squared minus 6x
Where are you at?
plus the n divided by 4. Okay, now watch, if I set up my window, if I just go up to window and choose x min to be 0 and x max to be 3, because that's my domain, right? Haley, where's Haley sit? There she is. If I just go zoom fit and let the calculator fit the y values, so zoom 0. Nice. Okay, well, what number do you suppose that is right there? 1 probably, huh?
Oh my god.
Okay, but then on your calculator, we can see that there's only one relative minimum there, right? Now watch this, if I go second calc, and I go up to minimum, I just have to put a left boundary and a right boundary, and I can just trace, or I could even just type in values, right? But I'll just trace for now. So if I just run the little ant over there. Okay, so I think he's right. So that's far enough. There's my left boundary. Okay, there's my right boundary. And my guess is just anywhere in between. Look what it tells me. Okay, I mean, what's it really trying to say there? 1. I mean, there's a little bit of a calculating error there that it makes. And that's because it's doing that algorithm. It's like a souped up version of Newton's method. And I will show you, I promise, don't let me forget. Before the end of the year, we'll come back and look at Newton's method, because it is pretty cool. But does that make sense? Okay. So you could always check your answers that way, but you got to be able to do them without a calculator too. So that was, okay, that was a hard one, admittedly. Unless there was some little mistake that just, but there couldn't have been because we got the right answer. So.
Way to fry my brain before.